Okay guys, let's take a look at our day 3 in polar. Let's kind of remind ourselves where we've been. The first day in polar we did a lot of review. We really just learned one thing that was new, the derivative of polar. We learned how to do that. The second day we worked on area of just a single polar curve. Today what we're going to do is we're going to work on a system of polar curves and find different areas. And we will actually do more with systems on day 4. So we spent a couple of days on systems. Just to let you know, with the graphing, I have a hard time when I'm graphing two of these polar curves telling them apart when I put them both in pencil. So just letting you know, I usually use like I don't know, like a colored pencil or some different color so that I can tell the two apart. It's going to be important as you calculate, as you figure out how to set up your integral, as you figure out how to draw it and what part to shade. It's going to be important that you're able to tell the two polar curves apart. So that just kind of a little heads up on that. So that's what I'm going to do. I'll do them in each color so that we can tell them apart. Alright, what we're going to do actually on both of these is we're just going to graph and set them up, and then we're going to set up the integral, and then we're going to stop. We're not going to actually integrate. We're going to spend our time working on the setup, the graphing and the setup of the integral. So let's take a look. The first one we're going to graph is 3 sine theta. So just like we've been doing for a few days, I would do a Cartesian graph of it. Let's see, our amplitude is 3, and just a regular period. Alright, so it's sine, so we would start here at the axis and then go up, down, and just a regular sine curve. Alright, so let's translate that to the polar graph. Okay, so at angle measure 0, we're at 0. Then at pi over 2, we are at 3. So that would be connected with a curve. Just keep in mind that we're looking at this area right here in the first quadrant. The R values are increasing, and as our angle measures increase until we hit 3. Then on the other side in the second quadrant, which is right between here, our R's are decreasing and our angle measure is still increasing. We're still rotating, and at pi we get back to 0. Okay. If I were to continue to graph, notice how the between pi and 2 pi, all of the R's are negative. So when I'm in the third and fourth quadrants, my R is negative, which puts me right back up into the first and second quadrant. We actually would be tracing what we just graphed if we finished. And we talked about it yesterday or the day before, where you can find the cycle or the period of a polar graph, but it's quite time consuming and really not worth taking the time right now. We just graph, and when we're finished with the graph we stop. So there is our first graph. The next one I'm going to put in red, the 2 minus sign. So let's see. So sine has been reflected over the x-axis, and it's up 2. So that means my axis is at 2. Let's see, the period is the same, so we're at pi and 2 pi. Okay, it's a negative sign, so we start at the axis, and then we go down, and then up. So it looks like this. Okay, so let's graph that one. So at angle measure 0, we are at 2. At angle measure pi over 2, we are at 1. and we are have a curve between there. The r values are just decreasing. Okay, then we go and look at pi. At pi, our r value is 2, so we still have a smooth curve going on. Let's see, when we get to 3 pi over 2, we are at 3. And again, a smooth curve going on around there. And as we go back to 2 pi, that is at 2. So it's kind of a flat looking circle. Alright, so let's see what they're wanting. They want us to sketch and set up an integral expression to find the area inside the blue graph and outside the red one. Okay, inside the blue and outside the red. So let's shade that area. So we want to be in the blue and not in the red. So we're looking at basically finding the area of this section right here. That's what we're wanting to do. Okay. So with system of equations, with intersecting equations, we've been working with that type of thing for years. We set them equal to each other to find where they intersect, right? I mean, that's what we do. We need to locate this point and this point. We need to know where that is so that we can find out where they intersect, so we can set up our integral. So let's do that. Let's set our two equations equal to each other. Those of us that are pretty strong in trig and remember solving equations from pre-cal, this is going to be fairly simple. Those of us that have forgotten may have a little bit more trouble, but they're usually not real complicated to solve. So we'd move the sine over, 4 sine theta, divide by 4. We get sine theta is a half. Now, we need to pay attention to our figure as to which values we want, where sine is a half. We want the angle measure in the first quadrant and the second quadrant is what we're looking for. And so I'm sure we all in here remember our unit circle. And sine is 1/2 at pi over 6 and 5 pi over 6. So those are our locations. Now what I would like to do, we're going to start developing a concept that sometimes causes students some trouble. I am going to draw a line segment at pi over 6 and 5 pi over 6. Okay, that's going to be important to us because that is the area that's between our angle measures. So I'm going to just draw a line segment out like this and this, so I can tell what area I'm collecting. Alright, if you would think about the inside of this as like a windshield wiper. I mean, probably most of us probably drive or at least have been in a car, right? We know what the windshield wipers look like. And so if the windshield wiper is connected here at the pole and sweeps, that is the area that is going to be collected. Okay? It's the area between this line and this line is what I'm going to collect. So you can think of it as, and I guess I'll use a different color. All of this area is what exists between pi over 6 and 5 pi over 6. All of that area exists in there. And so I want part of it, but I don't want all of it, right? I just want the yellow part. I don't want this part down here. So I'm going to have to set up my integral to where I can take that part out. Right, so let's do that. So the area is inside the blue one, right? So I really want to integrate between pi over 6 and 5 pi over 6 of the blue one. I mean, that's going to pick up the area for me, so that's the first thing that I would write. So half, I'll just use my formula, the formula for area. Half, let's see, from pi over 6 to 5 pi over 6 of the blue one, which is 3 sine theta squared d theta. Okay, that integral will pick up all of those orange lines. It's going to pick all of that up. You with me? It's going to calculate all of that. I don't want this part right here, so I need to take that part out. Okay? That part that exists inside of the red one, I need to take out. So I would subtract the again, our formula, 1/2 integral. I want to subtract this part in here, this orange piece. I can, I guess, outline it. Let's outline it in orange. I want to take this part out. And so we have to think, how would we take that out? We would take that out by subtracting the area inside the red one at that location, right? We're going to subtract from pi over 6 to 5 pi over 6 of the red one, which is that 2 minus sine squared. Now I started with probably one of the easiest ones we could think of. This one is fairly straightforward. I know you're probably thinking, oh my gosh, that's the easy one. But that's pretty straightforward, I think. Are we okay? So we basically are having to subtract the part of the area out that we don't want. Okay? All right, let's look at the second one. We just have 2 to work with today. All right, so let's draw these guys. So the first one, let's see, we have an amplitude of 3 and regular. Okay, it's cosine, so we start at 3 and then we go down here. So there's our cosine graph. So let's graph that little one. Alright, so to angle measure of 0, we go out to 3. Then when we're at pi over 2, we are at 0. And notice that between 0 and pi over 2, our R values are decreasing. So I'm basically going from 3 to 2 to 1 to 0. Then at pi over 2, we heading to pi, we are in negative R. So when my angle is in the second quadrant, my rings are negative. So I have to go across to the fourth quadrant to draw. And so it's going, and then I go back to 0 at, let's see where we are, at pi, I'm at negative 3, so that would be here. So basically that's my drawing. Again, on this one, if we continued from pi to 2 pi, we would just trace over what we just drew. Okay, so these particular ones only need 0 to pi to complete. Okay, and it's like a circle-y looking thing, and we're going to go with the one that I did. It should be a little fatter maybe, but we'll just go with that one. Okay, so let's look at the second one. Let's see, it's 1 plus cosine, so we're shifted up 1. Our axis is up. And it's cosine, so we start at 2. Just regular. Start at 2, go down. And we look like this. Okay, so we go over here. And at angle measure 0, we're at 2. Then at pi over 2, we're at 1. So it's a curve. Okay. Then at pi, we go to 0. And I'm hoping we recognize we don't draw straight lines. I have seen that before. Please don't do that. We don't draw a straight line down there. It means, and besides, in the second quadrant, look, I have a positive r in the second quadrant. I'm supposed to be in the second quadrant. So that's where we hopefully can identify it's one of those little cardioid things that looks like a heart. Alright, so at pi we're at 0. Then as I head to 3 pi over 2, I'm at 3 pi over 2, I'm at 1. Same scenario. I don't draw a straight line. I actually exist in the third quadrant. So we draw a little part in the third quadrant. Now let's see, we're at 3 pi over 2. From 3 pi over 2 to 2 pi. At 2 pi we are back to 2. So we just kind of curve back to 2. Okay. And again, the blue one should be a little bit fatter, but we're just going to go with that. So let's see what they want us to do. They want us to find the area of the common interior. So the part that we're going to be searching for is the common interior, which is this part right in here. The part that's inside of both is what we want. Okay? So first step, just like in the other one, we set them equal to each other and intersect them. So we have 3 cosine theta equals 1 plus cosine theta. I move the cosine over, gives me 2 cosine theta equals 1. So cosine theta is 1/2. Alright, so let's think about which quadrants we're interested in. So I think that's pretty clear. That's a first quadrant, and that should be at pi over 3. Kind of doesn't look like that, but that's where it should be. Now, in this fourth quadrant, I have two choices. I can rotate all the way around and get a positive value, or I can go backwards. The area that I want to collect is here. It's in here. So should I go a normal rotation through here, or should I go backwards? I should go backwards, right? Because it's going to collect whatever is in its path. And if I'm rotating around this way, that's really not picking up very much, is it? So I need this to be the negative rotation of that angle measure, which would be negative pi over 3. So those are the intersections that I want to work with. Now let's draw the straight line, like the line segment out from the pole. We are always going from the pole and through our points of intersection and see what's going on. Like that. Like that. Okay? So between negative pi over 3 and pi over 3, again, let's draw this in orange. It's going to go here and it's going to collect all of this. It's actually going to collect all the way out. Well, depending on what function I use. But that's the range of negative pi over 3 to pi over 3. It's that part right there. Okay. So, do we want to integrate the red one or the blue one? The red one, right? That's where the bulk of, now notice how I say bulk, that's where the bulk of the area is. I want you to look at the figure closely, and I hope that you're seeing that that's not all of the area, it's just most of it. Okay? What we have going on, which typically disturbs some students, is we have this little piece right here, and this little piece right here that's not included. Okay, you're taking a line segment and cutting through a round thing. It's not going to fit exactly inside. A line segment through a round thing. So we're going to have to deal with that in just a moment. Let's deal with the bulk of the area first. So the bulk of the area we're going to get by integrating from negative pi over 3 to pi over 3 of the red one. And that one is the 1 plus cosine theta squared. Now I'm missing some area. I'm missing those two slivers, so I need to add some more area in. Now what would happen if so it's inside the red one, or actually it's right here. It's actually inside the blue one, isn't it? Take a look at this little sliver right here. So it's inside the blue. So if I integrate the blue one from negative pi over 3 to pi over 3, am I going to get the two little slivers? No, I'm going to get all of this area. I'm going to get all of this. I don't want that. So what should I do? I'll tell you there, it's beautifully symmetrical. If I could get one of them, then I could double it. What I want to do is go from pi over 3 to 2 pi would be convenient. That would collect it. Might be a little far, but it doesn't matter. It's not going to collect something that's not there. What if I went from pi over 3 to 2 pi? I would pick up that little sliver right there. And I need two of them. Okay, so let's draw that radial line. We'll just, I guess, do that. So I'm going to go from here to here, and it's going to pick up all of that area. Okay, I don't want the red area, right? I want this little sliver that's in the blue one. I want to pick up that area. And I want actually two of them, because they're exactly the same size. I'm going to be able to get both of the slivers at once. And I'm going to go from pi over 3 to pi over 2 of the blue one. And the blue one is 3 cosine theta. And that would get me the rest of my area. Okay? All right.